Hello everyone, welcome to week 6 for Algebra 2A Live, a recording. We're going to be going over complex solutions to quadratic equations. For week 6 assignments, make sure you're looking through our textbook, you're watching this video, you're working on the paper pencil problems and any other assignments for this week in Canvas. Make sure you show your work and doing multiple times in each test. Improving your work, improving paper pencil assignments, all that good stuff. Here's what we're going to be learning this week. If I give you a radical expression, I want you to be able to perform operations such as addition, subtraction, multiplication, division. If I give you a quadratic equation, I want you to solve it by taking the square root of both sides, if possible. I want you to learn how to understand how complex numbers are used to represent solutions to quadratic equations. And then given complex expressions, perform operations such as addition, subtraction, multiplication, and division. Finally, we're going to solve quadratic equations by factoring or using square roots and use complex solutions when necessary. Okay, so let's review what we did last week. We started this whole section learning about quadratic equations, and we learned that all quadratic equations can be represented by y equals ax squared plus bx plus c. 3 terms, we need to have one of them be an x squared term, or at least a variable squared, but we could have a term to the first power and a constant term as well. Being able to know what a, b, and c are really helpful as far as the coefficients of each term. How to factor the trinomial into 2 binomials. We spent a lot of that time yesterday splitting it up and realizing how do we take 3 terms and rewrite it as 2 terms, or 2 binomials multiplied. We saw if we set it equal to 0, factoring was a legitimate method for being able to solve quadratic equations. And then we started working with simplifying and multiplying radical expressions together. So we're going to pick right up. Again, we practiced a lot with quadratic stuff. We're going to continue moving on with quadratic equations for this week. Let's start by adding radical expressions. We did multiplying, we did simplifying. How do we add or subtract radicals together? Well, to add or subtract radical expressions, the key idea is you need to have the same radical. Kind of like we need to have the same variable to be able to combine like terms, we need to have like radicals. In this first example, let's call this first example A right here, we have 5 times the square root of 3 minus 18 times the square root of 3. Notice both terms are being multiplied by the square root of 3. So it's easy to subtract these because we just have 5 minus 18 gives you negative 13 times the square root of 3. That's it. Problem B, however, the second example, is a little bit different because here I've got the square root of 2 and here I've got the square root of 8. Currently, those are not like radicals, so we need to simplify first to try and get like radicals. So the square root of 2, I can't simplify that, but let's look at the square root of 8 over here. To simplify it, I want to look for factors of 8 that I can square root. And 8 breaks down nicely into the square root of 4 times the square root of 2. And the square root of 4 is nice because it does square root. Square root of 4 is 2. And so the square root of 8 simplifies into 2 times the square root of 2. Well, now let's rewrite this whole problem. So it becomes 8x times the square root of 2 plus 9x, but instead of square root of 8, let's multiply it by 2 times the square root of 2. Well, I can simplify all that into 8x times the square root of 2 plus 18x times the square root of 2. Now we've got like radicals. Now we can focus on what's in the beginning. 8x plus 18x is going to be 26x times the square root of 2. Here we go, a couple examples of adding and subtracting radical expressions. Let's move on into dividing. So we did multiplying. Multiplying is easy, but dividing takes a little bit of work. We have to do a process called rationalizing the denominator. It's a big word there, right? But we're going to learn that skill. To rationalize the denominator, we don't necessarily just divide, but we multiply as a way to deal with division and rewrite what's going on. We multiply the numerator and denominator by the same number so that the square root portion no longer appears in the denominator. So let's think about this. So I don't want the square root to be in the bottom. If I have anywhere, I only want the square root in the numerator. So I'm going to multiply the bottom number by the square root of 30. What's going to happen? Well, the square root of 30 times the square root of 30 is sort of like saying what's the square root of 30 squared? It just ends up equaling 30. That works out pretty nice because now I don't have a square root in the denominator anymore. But I have to keep this thing the same, so I also multiply the numerator by the square root of 30, because now it's essentially just the same as multiplying by 1. And so I need to know what is the square root of 18 times the square root of 30. Well, that's going to be the square root of 540. Okay, we've successfully rearranged a little bit. There's no more square root in the denominator, but let's see if we can simplify 540. So what is the largest perfect square that goes into 540? Well, if I pull out my calculator, start doing some division, I can see that 540 divided by 36 equals 15. So I can rewrite this as the square root of 36 times the square root of 15, all divided by 30. And the square root of 36 is nice because it's just 6. 6 times the square root of 15 divided by 30. Okay, we simplified it. It looks a little bit nicer, but there's still more we can do. Watch this. 6 and 30, because this is all being multiplied together, I can reduce that down to 1 over 5, right? Simplifying the fraction. So the final result is it becomes the square root of 15 over 5. And although we didn't do any division, we just did a bunch of multiplication, this is a better answer. There's no more square root in the bottom, and that's the process of rationalizing the denominator. Okay, so we are comfortable with square roots now. Let's start using square roots to help us solve quadratic equations. Let's go through some examples of actually solving some other quadratics. So here I've got negative 5x squared plus 18 equals negative 57. Watch what I can do. Let's start rearranging this thing to try and get x by itself. I have plus 18, so subtract 18 from both sides. That goes to 0, so negative 5x squared has to equal negative 75. All right, I'm trying to get x by itself, so let's divide both sides by negative 5. And now we've got x squared equals positive 15. At this point, all we did was subtract the same thing from both sides and divide the same thing from both sides. But now to get x by itself, I've got this x squared, and I need to be able to undo it because I just want to know what is x. I'm trying to work backwards to get the solution here. To undo squaring, this is where I use square rooting. It's the inverse. They're opposites. If I take the square root of x squared, I'm left with just x. But if I square root the left side, I need to square root the right side of the equation, and x equals the square root of 15. Now I need to pause here because it actually equals positive square root of 15 or negative square root of 15. And we need to explain real quick this whole positive negative business because this is going to come up a lot this week and next week. Think about two numbers that when I square them equal 16. Hopefully you didn't have to think too hard, but you should know, okay, if I take 4 squared, that equals 16. But there's also negative 4. If I take negative 4 times negative 4 or square it, that also equals 16. So we see that when I'm working backwards to try and solve equations, I need to account for both the positive and the negative solutions, or the plus in the minus case, because there's two different numbers that when squared equals 16. Squaring turns both negative and positive into positive. So that's why we throw in this whole little plus or minus, because negative square root of 15 or positive square root of 15, when I square them, they'll both turn into 15. So there's our two solutions, all right? So x can be square root of 15 or x equals negative square root of 15. Both of those are solutions that I could put in for x into this thing and solve it out. And we solved it out by taking the square root of both sides at the appropriate point. Let's do another one. This one's a little bit different because I got a parentheses of stuff being squared in here, but we can still do kind of the same idea. So I'm going to draw my line down to help me get my algebra right. I'm going to slowly work this thing out to get a by itself. So I'm first going to divide both sides by 4, because right now everything's multiplied by 4 over there. I want to whittle away that 4. I'm left with a minus 3 squared equals 12. At this point, I have a minus 3, and it's all being squared. So I can't add 3 to both sides because it's locked into the parentheses. I need to deal with the squared first. So now is the time when I'm going to square root both sides. And I get a minus 3 equals plus or minus, got to count for both situations, the square root of 12. Now the square root of 12, hopefully you're done enough now where you can recognize, oh, that simplifies into 4 times 3 or 2 times the square root of 3. So we can simplify that radical right there. My last step is I'm going to add 3 to both sides, and a, my solution a is 3 plus 2 times the square root of 3, or a equals 3 minus 2 times the square root of 3. There's 2 solutions right here. So hopefully you're understanding that whole plus or minus thing and how it affects our 2 solutions. All right, so there's a couple examples of working through a quadratic equation, taking the square root of both sides and solving it out. So in summary, we can solve quadratic equations by factoring, only if it's possible. Sometimes you just can't factor it. You just can't get it there to be factored, but you can at least try. We can also solve quadratic equations now by square rooting, taking the square root of both sides. However, you probably noticed this only works if there's no bx term. What I mean by if there's something squared, if there's a variable squared, there's no other variables around that are not squared. For example, if I had this, 3x squared plus 4x equals 10, I can't combine these x values. I can't get just x squared by itself to square root. So I'm always stuck. This one would not work by factoring. This one would not work by square rooting. And then make sure you're checking your work on your Desmos calculator. Again, last week we did that. You can go to the Desmos calculator. You can graph what both sides of the equation and see kind of what's going on and make sure that your solution matches up as one of the points on the graph. All right, let's try and solve the following quadratic. What do we got here? I'm going to work to get x by itself. I'm going to add 11 to both sides. So now we've got negative 3x squared equals 27. I'm going to divide both sides by 3. Sorry, negative 3. Now we got x squared equals a negative 9. And cruising along with our process here, I'm going to divide both sides, or sorry, square root both sides. So x equals plus or minus the square root of negative 9. Now you can try this on your own, but what happens when you try and calculate the square root of negative 9? Your calculator will come back and say error or undefined, but it is not, you're not able to calculate it. It's sort of like trying to ask, hey, what number, if I square it, equals negative 9? And if you think about it, 3 doesn't work because 3 squared equals a positive 9, but negative 3 doesn't work because negative 3 squared equals positive 9 as well. Before, or typically in class at this point, you would say there are no real solutions, right? We're stuck. I can't take the square root of a negative number. Oh, but wait. We can now get to talk about solutions that are imaginary. Hopefully I just blew your mind a little bit, but yes, in math we do have real numbers and real solutions, and we also have imaginary numbers. An imaginary number, we have this whole variable, we have this thing I, and I is equal to the square root of -1. That allows us to do a whole lot more math that we previously would stop with, but we're now working with imaginary numbers. So if I have the square root of -9, well, I'm going to rewrite that as the square root of -1 times the square root of +9. So I'm pulling out this part that I can't deal with, and I'm calling that I. The square root of 9 now I can deal with. It's 3. And so if I combine those together, it just equals 3i. And I see, oh, it's an imaginary number. The square root of 72. Well, that's the square root of -1 times the square root of 72. The square root of 72 I can now work with and simplify. 36 times 2. So I could rewrite that as the square root of -1 times the square root of 36 times the square root of 2. And then I see really quickly there, if I keep simplifying it, the square root of -1 is just I. The square root of 36 is 6 times the square root of 2. And so that equals 6i times the square root of 2. And it is also an imaginary number. So we have real numbers and imaginary numbers to now deal with in math. And we combine them into one large set of numbers, and we call them complex numbers. Complex numbers include both a real part and an imaginary part, and they look something like this. So some examples are 6 is a complex number. It's also a real number, but it fits under as a complex number as well too. -15i is a complex number. It's only got an imaginary part. We could have 3 plus 4i is a complex number with both a real part and an imaginary part. You could have -1/2 I plus 10. But these are all examples of complex numbers. 0 would also be a complex number. Anytime you're dealing with real or imaginary numbers or combined, it's a complex number. So we got complex numbers. Let's talk about how to add, subtract, multiply, and divide these. We like that, right? Let's do an addition problem. I'm going to take 3 plus 5i minus 4 minus 11i. Subtraction, we actually kind of know already how to do this, right? I'm going to rewrite it without parentheses, 3 plus 5i, and I'm subtracting all of this. I got to distribute my negative. So I'm going to subtract 4 minus a negative turns into plus 11i. And watch what we could do. I can combine like terms just like I would with an algebra problem. 3 minus 4 turns into -1, and the 5i and 11i give me 16i. And there we go. We just successfully added those two numbers together, or will, subtraction in this case. But that's adding or subtracting. Treat I just like a variable. To multiply, we treat them like binomials, right? This looks familiar. So let's use the FOIL method. This 3 multiplies the 4 to get 12. This 3 also multiplies the -11 to get -33i. Then we switch to the next one. This 5i multiplies the 4 to get 20i. And this 5i multiplies the -11 to get -55i squared. Notice I got an I times an I, so it's going to be I squared. Okay, how do I simplify this thing down now? Well, we can combine the middle terms. -33i plus 20i gives me -13i. Still got 12 right here. What's going to be interesting is let's see what we can do with this I squared. Since I is just the square root of -1, if I square it, the result is it just becomes -1. So -55 times I squared becomes -55 times -1. Well, look at that. It just turned back into a real number again. So we now have 12 minus 13i plus 55 once I just multiply my negatives and deal with subtraction negative. But then 12 plus 55 gives me 67 minus 13i. And there we go. We just multiplied our two complex numbers together. Division is a little bit similar to how we did division with radicals. I need to multiply the numerator and denominator in such a way that I don't have any i's or imaginary parts in the denominator. So let's look at what we got here. Taking the same two numbers and dividing them, I'm going to multiply the bottom by the complex conjugate. What I mean by it, I'm going to have the 4. If I have a 4 in the beginning, I have a 4 there. If I have 11i, I'm going to multiply by an 11i. And the conjugate is going to be the opposite sign. If it's subtraction here, I'm going to do addition. If it's addition, I'm going to do subtraction. Watch what happens when I multiply these out on the bottom now. 4 times 4 is 16. 4 times 11i is going to be plus 44i. Negative 11 times 4 is going to be minus 44i. And negative 11 times positive 11 with the i's gives me negative 121 times I squared. This is why we multiply by the conjugate. It's related to all that work we did with multiplying in special cases. The 44i minus 44i turned to 0. We already know I squared becomes negative 1, so it's just 16 plus 121. And in the denominator, that combines to make 137. Whew, there's no more imaginary part. That's one solid real number. Took a lot of work though, right? Let's now deal with the numerator. If I multiply the bottom by 4 plus 11i, then I got to multiply the top by 4 plus 11i. So here we go. 3 times 4. Switch colors here. 3 times 4 is 12. 3 times 11 is plus 33i. 5i times 4 is plus 20i. And 5i times 11i is plus 55i squared. Some things we can simplify, right? Switch colors here. I've got 12 still. 33 plus 20i, those middle terms I can combine to get 53i. On the right, 55 times I squared is the same as plus negative 55. I forgot my I right there. So 12 minus 55 gives us negative 43, I believe. And so we have negative 43 plus 53i. Look at that. That is one complex number. We have a real part and an imaginary part, and if I wanted to, I could split it up this way, negative 43 over 137 plus 5i over 137. I can't really simplify these fractions down anymore, but that's how you do division with complex numbers. You multiply the numerator and denominator in just such a way that the denominator, you lose all your i's, and they simplify out. Okay, this is a little bit of fun. Whenever we get introduced with i's, it's always fun to think about powers of i's. So our goal is to be able to say, well, what is I to the 136 power? Let's first play around with some i's. We already know I squared is just the square root of negative 1. And we just call that I. I squared then, and we've already dealt with that, is the square root of negative 1 squared. And so that just becomes negative 1. Now what if I keep on going? What is I to the third power? Well, we get to use some of our exponent properties. I can rewrite I to the third as I squared times I to the first power, right? But I already know I squared is negative 1. We've already defined that. So that becomes negative 1 times I, which is just negative I. I, negative 1, negative I. And on to the next one. What is I to the fourth equal? I to the fourth, using exponent properties, is the same as I squared times I squared. But we know I squared is negative 1, so that's the same as saying, well, what is negative 1 times negative 1 equal? And that just equals positive 1. That's trippy. I take I, this imaginary number, and I take it to the fourth power, and it turns into 1. 1, 2, 3, 4 cases. Let's see what happens with I to the fifth. Well, I to the fifth I can rewrite as I to the fourth times 1I. But we already know I to the fourth is 1, so it's really just back to I. And there's our 4 cases. I, negative 1, negative I, positive 1, and then back to I again. If we did I to the fifth, that's I. I to the sixth would be the same as negative 1. I to the seventh would be negative I, just like I to the third. And I to the eighth would be 1 as well. The pattern goes 5, 6, 7, 8. If I had I to the ninth, that's the same as I to the fifth, which is the same as I to the first. It's just going to be I. If I have I to the 10th, it's equal to I to the sixth, it's the same as I squared. It's just going to be negative 1. And I think you kind of get the pattern now, right? It repeats every 4 powers of I. I to the 12th would be 1. So now that we can use all this information, let's revisit what I to the 136th power is. So I to the 136th power, to figure it out, I need to take 136, divide it by 4, and see what remainder that I have. So I'm going to do 136 on my calculator, divided by 4, and it goes in exactly 34 times with no remainder. Well, what that means then is 136 is divisible by 4, so I to the 136 is going to be the same as I to the fourth. It's just going to equal 1. Just like that. Let's do another example. What would I to the 77th be? Well, 77, 4 goes into 77 19 times with a remainder of 1. So with a remainder of 1 would put it as with a 1 power. So I to the 77th is the same as I to the first. It's just going to be I. There you go. There's a little bit of fun to play with. Hopefully you followed along with all the different powers of i's and working with this imaginary number I. The last problem I want to do is let's take another look at a quadratic equation. We're going to solve it out, and then we're going to use complex solutions when possible to actually work this thing out. Okay, so I'm going to draw my line. Let's solve it. I want to get x by itself. So right now, let's subtract 10 from both sides to get rid of what's being added or subtracted. So 2 times 3x minus 5 squared equals negative 40. Okay, let's divide both sides by 2. So 3x minus 5 squared equals negative 20. Slowly moving this thing down. Before I can tackle what's in the parentheses, I need to square root both sides. So I'm going to square root the square root there, and we get 3x minus 5 equals plus or minus the square root of negative 20. Ooh, I'm going to have a complex thing going on right here. Let's add 5 to both sides. Let's keep going for right now. And now we've got 3 times x equals 5 plus or minus the square root of negative 20. And for my last step, I'm going to divide both sides by 3. All right, so if I'm solving this thing out, x equals 5 plus or minus the square root of negative 20, all divided by 3. Now there's some work we can do to simplify this thing out here. The square root of 20, I can rewrite as the square root of positive 20 with an I, right? Take out the negative part and call it, that's now an imaginary part. And the square root of 20, 4 is a factor of 20, so I can simplify it into 4 times 5, but I can square root the 4 to get 2i times the square root of 5 over 3, and we have 5 plus or minus that. So my two solutions, I have two complex solutions. On one hand, if x equals 5 plus 2i times the square root of 5 divided by 3, that's one solution. And x equals 5 minus 2i times the square root of 5 divided by 3. That's my other complex solution. So I still have two solutions. These are what I would put in for my graph, or put in for x values to solve it out to get equal to negative 30. And that's how we use i's to help us solve and work with quadratics in a way that we just haven't been able to do that before. Okay, so let's review what we did. We reviewed a lot with radical expressions. You should now know how to add, subtract, multiply, and divide if I give you a radical problem, radical expressions. If I give you a quadratic equation, you should now be able to solve it by taking the square root of both sides. You should understand how complex numbers are used to represent solutions to quadratic equations. We have real solutions and complex solutions now. If I give you complex expressions, we now know how to add, subtract, multiply, and divide with complex numbers and what they are. And we can solve quadratic equations by either factoring, which we did a lot last week, or using square roots that you did this week, and recognizing when we need complex solutions. Okay, have fun working on the assignments this week. I look forward to meeting with all of you soon.